This video is going to be a little bit long. I'm going to try to fit in a whole bunch of solving equations all into one video. So if you want to skip around to different types of equations, I'll leave some links to certain parts of the video in the description box so you can jump around easily without having to listen to me talk for so long. I'm just going to start out with some problems like the first few on our test review that are asking you to solve for x. These are two different types of exponential equations that we may ask you to solve. The first one is one of our most basic types of equations. Really, you're just looking at your variable being an exponent, and the question is, how do we get it out of that position? Because right now, I'm not sure how to solve for that. One way that we did it before was if you notice that both of these numbers are some power of the same number, then you can actually just change the base, and that makes solving really quick and easy. But if it's not so nice, then you can use logs to change the way the equation is displayed, and that allows you to get to the x. So again, like I've said in the other videos, if you haven't watched the first video about how to change between logs and exponents, you may want to do that first, because I'm going to skip over the explanations and just write them as logs as we go along. So for this first one, and any other equation where the x is an exponent, you want to change it to a log. Now you can either rewrite it as a log, which will mean that it has a base of 4, which is not calculator friendly, or you can take the log of both sides, which is forcing it to be a base 10, which is calculator friendly. So that's a little bit preferred. Okay, so for this one, I'm going to take the log of both sides. So now that's a log base 10. You could also take the natural log of both sides, and that would just be a log base e, which is also pretty easy on your calculator since it's a button right on the front. Okay, now the reason I like doing this log thing is because we do have a property that says that if you have an exponent on the term inside of your log, you can bring it out front as a coefficient instead. That property only works when a couple of things are true. One, you have a log there. If it's just an exponential like this, you can't just move the exponent down out front. And second thing, that exponent has to be acting on the entirety of the input of that log. So you can't have a second number out front and then just bring this exponent out. You would have to split that log apart and then bring the exponent down. So hopefully I'll be able to bring one up, or let's just write one. Here's an example of what I'm talking about. If you had a log base 10, 4 times 5x, you could not write that as x times log base 10 4 times 5. That's completely changing the value. What you could do is split this log apart first and then bring the x down on the one that it still applies to. Okay, so now we're going to take that x plus 2 down. All right. And now that basically makes the x accessible to us. And if you remember that logs are just numbers, really all this is a number that can be distributed to the x plus 2, or you can think of it as a number that's kind of in the way. Right now it's being multiplied, so to get rid of it on that side, we can divide both sides by log of 4. That actually turns out to be the easiest way to write this, so that's where I'm going to go. They're both equivalent in the end, but whatever's easiest to write is the direction I like to travel. Okay, so that means we just have x plus 2 on one side, and the only thing we have left to do is just subtract 2 from both sides. Now, I always like to write these down in the exact terms just so that I can keep track of my mistakes, because otherwise everything is a decimal along the way. I'm rounding. It's really hard to see where an error occurred if I need to go back. But this is pretty clear what exactly I'm doing, and then I can type all of that into the calculator at once. Okay, so I have my calculator here, and hopefully you'll be able to see exactly what I'm typing in. I'll try to angle it. We're going to do log 45 over log 4 minus 2. Now the reason I chose log base 10 is because it's actually a button right here. If you had done log base e, you could use the natural log right here. I would not rely on being able to change the base just because it's inconvenient and not all calculators have that function. Okay, so here log 45 divided by log 4. And then you can do minus 2 right away, but I like to just hit enter and make sure that I'm doing the order of operations that I want, just in case the calculator is being finicky or if I missed a parenthesis or something like that. Okay, so for this one I got x equals this long decimal. We're typically going to ask you to round to 4 digits, so I'm just going to round this one. I know the answer doesn't matter too much, but it might be good for you to practice along with me. All right. Now the second one is a very similar looking example, but it makes it a little bit more complicated because once you've changed it to a log, you're going to end up with an x on both sides. And even in algebra, you know, a really simple looking linear equation, if you have an x on both sides, you have a couple of extra steps that you have to take care of. So that's going to be the same case here. And again, I like to write everything as logs and keep it that way throughout the process just so we can keep track of what's going on. You can definitely round, you know, just type things in as decimals, and that allows you to combine things nicely. But make sure you're rounding extra numbers or extra digits so that when you round in the end, your answer is still as accurate as we would like it to be. So here I'm going to approach the same way because the x is an exponent. You'll hear me say that a bunch, but every time x is an exponent, the best way to take it down is to take the log of both sides. So that's just where we're going to start. Now again, you have a choice. You can do log of any base technically, but for the calculator's purposes, a log base 10 or a log base e work out really nicely. And then just like I did on this problem, now that we have a log on both sides, we are allowed to use that property where we can take the exponent and bring it forward. And because that exponent is acting on the entire input, there's nothing extra in here, I can actually bring it forward. All right, so now here's where we deviate a little bit. You can divide away the log on both sides, but I mean, basically you can see right here, as soon as you do that, you end up with a fraction. And I know that I'm going to have to distribute at some point or move the x's from side to side, and I really don't want to write fractions a bunch of times. So I'm just going to distribute at this point only because of personal preference. You can do this a ton of different ways. Just make sure you're keeping track of how you would do this algebraically. These are just coefficients, so treat them as such and do whatever you feel comfortable with, but make sure everything you do is valid. I don't know if there's much that you can do to mess up at this point. It's really just these properties that are a little bit challenging. Okay, so distributing in the log. And this is the part where it starts to look ugly just because there's a lot of writing, but everything is very organized. And as long as I have logs there, I'm not seeing too many numbers. I'm just trying to keep everything organized. Now I look around and I notice that there are two terms with an x. And just like any other algebraic equation, we're going to try to group those on one side so that we can combine them and get the x by itself. So I'm going to subtract and move everything to the left. I think I've told my students this in class. There's no particular reason for me moving things to the left. I just have done that by habit, always kept the variable on the left side. And then I'm also going to move the constant on this side to the other side. So subtracting away 2 log 4. And that's again just because if we had a similar algebraic equation, we would be moving all of the numbers to the other side away from the x's. Okay, so now this is a really big number. If I typed it into my calculator, it would come out as a single number. So I'm just going to think of that as a constant. Over here, I've got 2 x's, and unfortunately, I can't subtract those and get a number just because I'm not typing them into the calculator. So another way to get the x's separated is to factor out the x from each term, and that separates the x's away from the numbers that they're multiplied to. All right, and again, if you're thinking of logs as numbers, which they are, this whole term right here looks really complicated, but that is just a number. So it is a number times x, which means it's just a coefficient, and just like any other coefficient, we can divide it away from that side to get the x by itself. So that's what I'm going to do next. Okay, that gets our x by itself. And now I can type everything that's left into the calculator to get my final answer. Again, along the way, you may have typed in your logs, gotten decimals, depends on your teacher and what they prefer. I really need the answers to be as exact as possible. So if you do type these into the calculator, make sure you're writing down more digits than what you need or storing it in your calculator along the way so you can use a variable, whatever you need to do, but try and keep that answer as exact as possible. Okay, so typing this all in, I do need to use parentheses around both the numerator and the denominator. Otherwise, the calculator will try to divide before it adds and subtracts. So I'm going to do parentheses log 45. Hopefully you can see that. I'm having trouble seeing. Log 4. Okay, so there's my numerator with parentheses. Then divide the denominator. With parentheses. Looks messy, but it's all exact at this point. And that is as exact of an answer as we can get with decimals. So negative 0.4272. All right, the next problem that I wanted to look at is also an exponential type of problem, but it's a totally different approach. This one is involving a term that is common, or an expression that is common within each term of this equation. This common term can look like anything it wants to. It doesn't even have to be an exponential. It's just probably going to be because that's the unit we're working on. But there is a common expression in every single term. If there is something like that, common in every single term, you can factor it apart. The first thing I'm going to do is, now that I've circled that, you may notice that the things that are left form a quadratic equation. So I know that I'm going to have to use quadratics in here, which means I need 0 on one side. I also know that I don't necessarily want to divide this away from both sides because it may contain a solution. And if I divide it away from both sides, then I don't get that solution. In most of these cases, I think all the ones we've done, this term that's common doesn't actually give you a solution, but you never know. There could be a variation of this problem that does include something that may have a solution. So you do not want to divide it away, but we can factor it apart so that we can treat it as a separate factor. So like I said, it's quadratic, so we want to get 0 on one side. I'm going to move this one from the right to the left first. Then we can factor out that common term. So factoring out the 3 to the 3x, we're left with that quadratic that we had. So that's one factor. Then you want to check and see, is that quadratic one factorable? If it is, then it makes your life a little bit easier. If it's not, you will have to solve using quadratic formula. But essentially what we're doing at this point is using a zero product property. If we have two things that are multiplied that are equal to 0, then we can assume that at least one of them is 0. So we're going to set each factor equal to 0. And that's how we get that mini little quadratic embedded in this equation. Over here, if you're unsure how to solve this, you can take the log of both sides, but it actually may be something that you remember. There isn't a way to have a power of 3 that equals 0. Even if that power was 0, it would equal 1. There is no way to get a 0 out of this. So no x is going to cause this statement to be true, which means in this case we do not get a solution from that part. But like I said before, you always want to check in case we, made it something different. It might have a solution embedded there. So now we're looking on this side for any solutions we can get from the quadratic. This one is 6 and 1, 2 and 3, not factorable. So we're going to have to use quadratic formula. Negative b plus or minus square root b squared minus 4ac, all of that over 2a, and then simplify. Nope, 28. So then that will simplify into 2 and 7. And then we can cross out a 2 from every single term. Okay. And so those are two possible solutions. Now, I mentioned one time before that you do want to check all of your solutions and make sure that they're valid. I didn't mention that up here just because I'm about to say why we also don't need to check these. If you have an exponential as your original equation, any x that you can think of can actually go into that function and you can get an output. Exponentials don't care. You can evaluate a negative exponent, you can evaluate an exponent of 0, and positives are always fine. So we don't really care what these came out to be. We didn't really need to check. The same thing actually applies here. Even though there are two solutions, because the original problem was either quadratic or exponential, it does not matter what the x is. We can evaluate any part of that equation with any x that you can think of. So both of these are valid solutions. So we can say that those are our two solutions. The next one that we have on here is a log, so that means exactly what I just said is going to be important this time. We will have to check the solutions that we get in the end because logs are not okay with any input. We cannot evaluate a log if the input is negative or 0, so we're going to have to be aware of that when we get to the end. So here I've got the opposite problem. In all the other problems, our x was an exponent, and it was hard to get it out if it doesn't have a common base. So here we actually have a different problem. The x is embedded in a log, and that's even more difficult to get out because we can't evaluate the inside of a log, or sometimes we can, but not always. We can't always just evaluate the inside of a log unless it's guess and check. So the best way to get the x out of a log is by changing it over to an exponent. But even here, we still have a problem. We can't change this to an exponent in the form that it's in right now because we have two different logs on this side and a log on the other side. So we need to figure out a way to combine them. So then we can either compare the two sides or we can change it to an exponent at that point. So here we need to actually use a log property. There is one where if you have two logs that are being added together and they have the same base, then you can combine them into one log as a product of their inputs. So that's what we're going to do here with these two. I'm going to combine these two logs. They both have a base 10 since we don't have anything written there. So the new one also has a base 10. And the input is going to be the product of these two inputs. So x times 2x and x times 1. All right. So now I would normally say, let's just change this over to an exponential because we have an x inside of a log. But there's actually an even quicker way to do this one because there's a log on both sides. We can evaluate the insides, those inputs, and set them equal to each other because the logs are the same on both sides and the two sides must be equal. So I'm just going to ignore the logs for now, kind of undoing that log of both sides property, just going to look at the inputs. Set them equal to each other. And I notice that it's quadratic. So just like in the previous one, if it's quadratic, we want to try to get 0 on one side so then we can solve it using factoring or quadratic formula. I believe this one is factorable. Let's try it. 6, 3 and 2, 4 and 3. Yep. Hopefully that's right. Leave me a comment if it's wrong. So now we have it in two factors, just like we did on the previous problem. We can set each factor equal to 0. And then over here we get x equals -2. So there's two potential solutions. Now I mentioned at the beginning you have to check and make sure that both of those or even one of them works inside the logs of the original problem. I can tell right away that this one won't because we have one log here that just has x for the input. If x is negative, we're not going to get a real output. So that is not allowed. The second one, I want to double check. 3/2 is positive, so that's okay with this first log. And the second log also has all positives, so we should be fine. This is our only solution from this problem. And our last example is also like a problem on the test review. This is another exponential example. This case, it is a little less obvious, but this is actually another quadratic problem. It's just kind of a quadratic embedded with a weird base other than x. So the first thing that I notice is that we have, ooh, I made a mistake here. This should be a 3. Good catch. Okay, so what I was going to say was we have the same base on either side. So in the very first lesson, a long time ago, we talked about how if you're solving exponentials and they have the same base, or you can create the same base on either side, then you can compare their exponents. That's equivalent to what we did in that last problem where we had a log on both sides, and it was the same log base, so we could compare their insides. Same idea, but with exponentials. So I do notice that I have the same base, which is good news. Now I just need to get it set up so that there's only one on either side. That way I can compare the two directly. So I'm looking at the left side and trying to see, is there a way that I can combine those together to create one base of 3? And there is. This first one has a power of a power, which is when you multiply the two exponents, so that would be an x squared. Then I have two bases that are being multiplied and they're the same, so I add their exponents. So to combine those together, I have x squared plus 4x. Now since the bases match, we can compare their exponents directly, and that's another quadratic. And just like every other one in the past, I'll move everything to one side so it's equal to 0. And then see if you can factor. That's the best way to do it, but if you can't, then you can use quadratic formula. Again, I believe this one is factorable, plus 6 and minus 2. Set each factor equal to 0, and solve for x. And since the original problem was exponential and not log, then both of these are okay as solutions. I hope this helped. Let me know if there's any other types of problems you would like to see. I can make a separate video.